Can exomoons be habitable? Do hypervelocity stars leave a wake? And how thick is the event horizon of a black hole? All this and more in this week's Question Show. Hey everyone, welcome to the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I will answer them here. A reminder, I record this show every Monday at 5 p.m. Pacific time. So if you want to have the live experience, like actually see me and interact with me and the rest of the people who are watching the show, then come join us every Monday at 5 p.m. Pacific. There will be a event somewhere here on my channel. Make sure you subscribe to the channel, you click on the reminder, and as I told you last week, I promise that YouTube will unfailingly remind you when the live show begins, and you won't have to, but you kind of can bookmark it and watch it later if you kind of know what you're doing, but we make it unlisted and then bring it, and then we edit it into the question show that you're watching right now. All right, let's get into the questions. Spartak Baliu 8048. If a planet with the size of many times bigger than Jupiter has a moon the size of the Earth and orbits a red dwarf in the habitable zone, could that moon support life as we know it? Absolutely. In fact, it could be one of the few ways that you could have a nicely habitable world close to a red dwarf star. So let me explain the problem with red dwarfs. I mean, the one big problem, and we're not going to find a solution for it here, is that they are very testy in their youth. They can throw out really powerful solar flares. I mean, the solar flares are like the same kind of power as the ones that we have from a star like our sun, but the star is much smaller and the planets have to be huddled much closer to the star, and so the damage from these solar flares can be devastating. Hundreds of thousands of times more powerful and more impactful on the planet than anything the sun can throw our way. So that is the big problem. It is an unsolved problem. We do not know if worlds are habitable close to red dwarf stars. But one of the other problems, and this is probably surmountable, this is probably survivable, but it's not going to make for a great planet. And that is that terrestrial planets orbiting around red dwarf stars are almost inevitably tidally locked, which means that they're always going to show one face to the star. And so you're going to get one side of the planet very hot, and then the other side of the planet is in complete darkness, and so it's going to get cold. Now, the part that's facing the sun, it's not going to be like a bone-dry desert. It's probably going to be more like an eternal swamp. Very humid, very rainy, very foggy. It's going to be probably habitable though, but the best places are going to be around the margins in between the day side and the night side. Still, not the greatest planet when half of your planet can't be used for life as we know it. But if you have a moon that is orbiting around a giant planet like Jupiter, suddenly everything changes. Yes, the moon is probably going to be tidally locked to the planet, so it's always going to be showing one face to the big giant Jupiter-like planet, gas giant that it's orbiting around. And maybe the gas giant is tidally locked to the star, but the moon is orbiting around the planet. And so as it goes around, it's going to go through a day-night cycle, kind of in the same way that the moon goes through when it orbits around the Earth. Now, of course, the day on the moon is like half a month, and a night on the moon is half a month, which is not great, but still, it's better than nothing. And so you would get very long days, very long nights, and you would have some level of habitability, like as long as you're in that habitable zone. The minimum size to probably get a gas giant planet orbiting around a red dwarf star is about 20% the mass of the sun. So if you've got something that is less than 20% the mass of the sun, and red dwarfs can go down to like 7% the mass of the sun. So as long as you are above 20%, then you can get one of these gas giants. And if you can get a gas giant, you can get these Earth-sized moons orbiting around it. But the moon doesn't have to be Earth-sized. It can be smaller. Like pretty much, if you could get a moon as big as, say, Ganymede, at the very least, then it would have the gravity and possibly even a magnetosphere that would be able to hold its atmosphere against the solar wind. Like a regular solar wind, not killer solar flare solar wind, but a regular solar wind against its star. And so it would be able to maintain an atmosphere forever. So yes, an exomoon is a really exciting candidate for life orbiting around some other star. And right now we have no concrete guarantee that we know of an exomoon around another planet. There have been about 24 candidate exomoons that have been found, but we haven't got any conclusive evidence. So, I mean, this is one of those discoveries that is right around the corner. Probably within the next 5 years, we will get this conclusive evidence of someone finding a exomoon around a gas giant orbiting around a star, and then probably within a few years after that, we will learn of an exomoon in the habitable zone of a red dwarf star or some other star. And that's going to be really exciting. Like, I think it's going to be as exciting as finding a terrestrial planet around a red dwarf star in the habitable zone. So stay tuned for that. All right, I'm sure you've noticed the planet names that are above one of my shoulders. I'm going to guess it's this one. And this is a way for you to vote on which question you thought was the best one, which answer was the best one, the sort of hybrid question-answer combo team. And last week, the top voted question was for David's Dream Factory, asking if there was a potential habitable zone around a black hole's accretion disk. So congratulations to David's Dream Factory and congratulations to me for the answer. Together, we made a great team. Now, don't forget, vote, put down the name of the planet that you liked the question the best. We'll count them up and we will celebrate the winner next week. David McSween. Do hyperstars leave a wake that we could detect closer to light speed? Could they have a damaging bow wave? All right, a couple of weeks ago, someone asked a question about hypervelocity stars, and so we went into an answer on that. And now you're doing a follow-up question. Can they leave a bow wake? And the answer is yes, absolutely. Now, I don't know of any examples of a hypervelocity star that is leaving a bow wake, but we know of several regular stars that are leaving a bow wake. And so there's a couple of examples. One, and this is research that was done about 15 years ago. These are some images of stars that were captured by the Hubble Space Telescope. And these are stars that are moving through a nebula and they are leaving a bow wake. Another fairly famous star is called Mira, and it's sort of, you've heard the term Mira variables. It's a, sort of defined a certain class of variable stars. And this star is moving through the interstellar medium at about 130 kilometers per second, which is like 1/10 the speed of the hypervelocity stars. So it's not leaving the Milky Way, but it's moving pretty quickly. And about 15 years ago, astronomers were able to detect a tail behind the star, like a comet-like tail, and a bow wake in front of it. There was a piece of research that came out on Archive today, like when I'm recording this, which is why I picked this question. And that is that astronomers think they found a supermassive black hole that is moving on a hypervelocity trajectory, and it is leaving a bow wake. So how do you get a supermassive black hole on a hypervelocity trajectory? Like, that sounds terrifying. And so what seems to happen is, like, when two galaxies collide, you get the black holes finding one another in the collision because they sort of sink down to the center of this tangled up, collided mess. And when they find each other, they can either merge into one much larger black hole, one more massive black hole, but another possibility is that the smaller black hole will get recoiled away from the center of the other black hole. And so it doesn't actually merge, it gets kicked out, and now it's on this escape velocity. Like, wrap your mind around this for a second. There are supermassive black holes, so black holes with millions, sometimes even billion times the mass of the sun, that are moving on a hypervelocity trajectory in a random direction, just moving through the universe. And so this black hole seems to be going at about 1,600 kilometers per second, which is sort of the same speed as those hypervelocity stars that we mentioned in that other episode. And once again, it was detected partly because astronomers were able to find the bow wake in front of it, and they were able to detect the wake behind it. And what it's leaving in its wake is a mess. It's leaving sort of compressed clouds of gas and dust and star formation, which makes total sense. Like when you get star-forming nebulae, they need some kind of kick to start collapsing these cold clouds of gas, and having a black hole move through the vicinity and using its gravity to influence the collapse of these gas clouds and create new star formation makes sense. So stars leave wakes. I mean, it depends on what they're moving through. What's the medium? Are they moving through a nebula, or are they surrounded by some kind of gas and dust? If so, yeah, they'll produce a wake. They'll create some kind of bow wave in front of it. I don't know if it's damaging, but as I said, with the supermassive black hole, you can get this collapse of gas and dust and get star formation. So like it's a creating bow wake as opposed to a destructive one. Although I guess if the black hole gets too close, it's a bad day. Cole 0342. What is the thickness of the event horizon of a black hole? Like we've talked in the past how the event horizons of different black holes change based on the mass of the black hole. So if you have a stellar mass black hole, maybe the event horizon is only a few kilometers across. If you have a supermassive black hole, then maybe the event horizon is like the size of the solar system. And based on the size of that event horizon, the tidal forces that you experience as you get closer and closer to the black hole can be dramatically different. So as you're getting closer to a stellar mass black hole, the tidal forces can tear you into pieces, spaghettify you, and turn you into this long string of material that is wrapping around the black hole. But if you approach a supermassive black hole, you might cross through the event horizon and not even feel it, because the gradient of the gravity that you're experiencing is so low that the tidal forces, like there are tidal forces, but they're just not strong enough to start snapping you into pieces. And you have crossed the event horizon, you are inevitably going to be going into the black hole. And so like, is there a size to the event horizon? And the answer is no. That the event horizon is like this mathematical place where if you have light that is getting really close to the black hole, then it's either going to go in or it's going to be able to orbit around the black hole. And if you had something that emitted photons that was just outside the event horizon, then its photons would take this curved trajectory. Some would be able to reach space, others would curve around and then be gobbled up by the black hole. And as you bring this source of photons closer and closer and closer to the black hole, once you get within, say, I don't know, a few meters, it's going to be, the light is going to be making most of its way around the black hole. But then you're going to get close enough where all of the photons, no matter where they go, they're just popping out, even if they're exactly opposite to the black hole, and they're getting pulled in. And that is the event horizon. It is not thick, zero thickness, and yet it is this place. When you're outside of it, photons get out of black holes. When you're inside of it, then even photons, light itself, can't go fast enough to escape the pull of a black hole. Swamp Matt. If our sun magically ceased to exist, how long would it take before our orbital path would be affected? What is the speed of gravity? So light takes just over 8 minutes to get from the sun to the Earth. And so if the sun disappeared, you wouldn't know about it for just over 8 minutes before the light reached Earth. And then suddenly 8 minutes after the sun had been removed, the sun would disappear in our sky and we would start to get cold. But the question is, what about the gravity? So back in the day, people thought there was maybe a couple of possibilities. One possibility is that gravity moved instantaneously. And so if you disappeared the sun, then Earth would immediately start moving in a straight line without that gravitational anchor. The other possibility is that gravity moves at some kind of speed, faster than the speed of light, slower than the speed of light. And then the other possibility is that gravity moves at the speed of light. And it's been a fairly tricky question to figure out, because you can't just make stars disappear. You have to figure out a way to be able to perform an experiment. And people were able to get approximations at the speed of gravity. They're able to use things like watching as Jupiter's moons passed in front of the planet and then watched the transit, but also were able to measure the gravity of Jupiter to the world to try and figure out what the answer was. And they got a number that was kind of similar to the speed of light, but they weren't entirely sure. But in 2017, we got absolute and total proof that the speed of gravity is the same as the speed of light. And that was because of the kilonova. And this is when astronomers saw two neutron stars collide with each other. And they detected the gravitational waves of this collision with LIGO, and then they were able to pinpoint in the sky where this object should be. And astronomers turned their telescopes into this region, and they saw the visible light, the radiation coming from the object of the neutron stars colliding with each other. It's a type of gamma ray burst. And so then they did the math, and they said, okay, well, we've seen, when did the gravitational waves arrive from this collision? And when they timed everything out, the gravitational waves began as within the few final seconds as these two neutron stars were swirling around each other and about to collide. And then the moment after they collided, then we saw the visible light radiation in the sky. And that just proved once and for all, forever, that the speed of gravity is the speed of light. And it's like the most beautiful example of having what was a question just be solidified to an answer. And this is the magic of multi-messenger astronomy, this way of seeing the sky in different ways. On the one hand, you've got the electromagnetic spectrum. And so, like, when we look through a telescope, when we look at infrared radiation, when we detect X-rays, gamma rays, radio waves, it's all versions of the electromagnetic spectrum. And so it's not truly multi-messenger. If you're looking at something in ultraviolet and in radio waves, you're just seeing two aspects of the same phenomenon. But when you measure the gravity waves coming from some collision, it's a completely different way, and it has the chance to transform astronomy. There's one other method, which is being able to detect neutrinos. And if we can get to a point where we can really reliably detect things with neutrinos, with gravitational waves, and with electromagnetic radiation, you will have three different independent methods of measuring things in the universe, and astronomy will move from very wide error bars into a great deal of precision. And this is why you're seeing powerful new gravitational wave observatories coming online, like the LISA mission that's going to be sending gravitational wave observatories to space. And you've got upgrades to the ice cube facility down in Antarctica, going from 1 cubic kilometer of ice to 10 cubic kilometers of ice, and other ideas for building neutrino detectors as well. So like, the future is multi-messenger. I'm really excited about that. And it's one of the ways that we learned one of the bigger mysteries in astronomy in just a couple of years ago. If you like my answers to your questions, as well as the other things that we do at Universe Today, consider joining our Patreon club. This allows us to keep minimum ads for everybody. Like, as you can see, there are no ads during this video. As a patron, you'll also get an ad-free experience on universetoday.com for life. Even if you unsubscribe, you'll get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. And thanks to everyone who has already subscribed, and welcome to our recent newcomers: Marcel, Eric, Jan Cornell, Jeff, Bertrand Berlaire, Alan Case, Patrick Redding, Scott Burton, Mystery Crumble, and Bob Moeller. Join the club at patreon.com/universetoday. Chris Lang, if our large rogue planet, something the size of Jupiter, came flying into our solar system and crashed directly into our sun, what would the consequences be? Would it move or damage the sun? It's almost certain that the sun has gobbled up planets in the past and could very well gobble up planets in the future. I don't know about rogue planets, but even if a rogue planet passed through the solar system, which is a fairly large region when you really think about it, like a couple of light years out to the farthest reaches of the Oort cloud, that's a big region. You could definitely have rogue planets passing through that region. But to deliver a bullseye to the sun is going to be incredibly rare. But if a rogue planet did pass through and hit the sun, nothing would happen. It would gobble it up. So no, it wouldn't be a big problem, but it would be detectable. So astronomers have been able to scan the atmospheres of various stars, and they've been able to find the chemicals from planets that star might have eaten over the last, say, billion years or so. And that's kind of cool. Now, it wouldn't be a rogue planet. Like, it would almost certainly be that the star ate one of its planets. But the bigger issue would be the planet moving through the solar system itself, the gravity of that planet. Like if you had a Jupiter-sized planet that was slowly making its way through the inner solar system, the gravitational interactions from that would be catastrophic. It would shift objects out of their orbits. It would cause potentially some planets to be thrown out of the solar system entirely, other planets to be thrown into the sun. It would be a very bad day. I feel like I'm underselling the damage, right? It would be catastrophic damage to a solar system. And we see examples of exoplanetary systems that are weird. And so we wonder if maybe something catastrophic happened to that star system. So there's one example that we just posted on Universe Today where the planet is orbiting around the poles of its star. It's on a polar orbit. Now, normally, like all planetary systems are lined up around the equator of the star. Like think about the solar system, right? The star is turning, the planets are lined up like this big disk around it. But imagine what would it take to have a star turning one way and yet have a planet that is orbiting pole to pole over top of it. Something catastrophic. And that's not the first time that we've seen this. Astronomers have seen several cases of these planets that are on these really highly inclined orbits. And it probably came from some kind of gravitational interaction, a star getting too close, a planet getting too close, and mayhem ensued. So I wouldn't be worried about the star. Like if a planet fell into the star can handle that. I would be worried about all of the planets, all of the moons, everything else that is associated. Hiram Cricklow, have there ever been fish on the space station? How would microgravity affect an organism that lives in water? Great question. And this is a test that has been done. During the Apollo era on the Skylab space station, astronauts brought up a bunch of fish. They brought a couple of juvenile fish and they brought a bunch of fish eggs. And so they were going to see what would happen to the fish on board the space station in microgravity. And the fish hatched and were able to swim around, but they did a lot of looping around. And the problem was that they couldn't feel gravity. So even though like when you're swimming underwater and you're being held buoyant, your internal organs are still experiencing gravity. And so you can orient yourself and know which way is up and which way is down because you have this internal sensation of gravity. But once you're in space, you don't have that sense, and the fish didn't have it, and the fish were sort of swimming around upside down, going in circles, trying to get a sense of where they were and what they were doing. But what's interesting is they adapted fairly quickly and they were able to associate light with up. And so they were able to figure out that wherever the light part of their tank was, that's where up was. And then they oriented themselves to that way. And so, you know, I mean, there haven't been excessive long-term experiments with fish in space, but it sounds like they're okay and they can work out how to deal with it much better than we can or other animals. You know, if you see spiders spinning a web in space, it's pretty crazy. And like there have been a lot of animals that have been to space, and fish are just one of them. Googler, how do we know that black holes are near absolute zero on the inside? We don't know the temperature of black holes inside the event horizon. Like if you're going to measure a black hole, you can only figure out 3 pieces of information. You can figure out its mass, you can figure out its spin, and you can figure out its overall magnetic field. That's it. You can't figure out what's going on inside the event horizon, or if there's a way to do it, nobody's figured it out yet. And so you don't know what the temperature is. Like you can imagine all kinds of different scenarios about what's going on inside a black hole event horizon. Like maybe it's some object like a neutron star that's just a little bit smaller than the event horizon. But if you did pass through the event horizon of that supermassive black hole that I talked about at the beginning, you would bonk into the surface of the black hole. But maybe it's tiny, that all of that mass of that entire star, tens of millions of times the mass of the sun, is compressed down into an object that is the size of an atom or at the Planck scale. Or maybe it is just continuing to collapse, getting denser and denser and denser and speeding up. reaching levels of density we can't even comprehend, and it's accelerating its density. Is there heat inside? We don't know. All right, different models. I mean, there's this idea of like a firewall inside the event horizon that if you crossed into that, you would be destroyed. But there's, the tidal forces, lots of ways to destroy you. But we do know that black holes have a temperature from an exterior point of view. So when you are looking at a black hole from outside the black hole, you can measure the temperature of the black hole. And most of the time, that temperature is going to be close to absolute zero. It is not giving off any radiation. The more massive the black hole, the less radiation that it's giving off. But as a black hole gets smaller and smaller, it gives off more and more radiation. This is Hawking radiation. And so when it is like the size of a small asteroid, it might be room temperature. And then when it's the size of a house, it could be really hot. And then it finally gives off a final blast of gamma radiation and disappears. David Guy, how much do we actually know about Proxima Centauri? Quite a bit, but not as much as we'd like. So we know that Proxima Centauri is the closest star to the sun. It is in a three-body interaction with the stars of Alpha Centauri. So Alpha Centauri are actually two stars that orbit around each other. And then Proxima Centauri is a third star that orbits in a very wide orbit. It's actually the star system that's featured in the three-body problem series, although it's not unstable. And if you had planets orbiting around it, they wouldn't go through this weird three-body interaction. We know that the star is a flare star and can send out fairly powerful solar flares like most red dwarfs do. And we know that it has planets, at least 3 that have been detected so far, 1 in the habitable zone for sure. So that's really interesting. It's pretty exciting that the closest star to the sun has a planet and it's in the habitable zone. And so if we want like a target to be able to see, it's probably the easiest one that we could probably look at. Almost certainly someone has used James Webb already to do images of Proxima Centauri. Now it's just a matter of time before they release those results and we learn about it. And I can imagine future telescopes being directed only at Proxima Centauri for long periods of time to try and figure out more information about the planets that are orbiting around it. San Mateo. Is it possible for a rogue planet drifting through space to have an atmosphere? Yes, it is possible for a rogue planet to have an atmosphere. So let's talk about this idea of rogue planets, right? There are planets orbiting around the sun and they are warmed by the sun, the terrestrial planets, right? And when you think about as you get farther away, colder, things start to freeze up and you get these ice planets around Jupiter and Saturn, all the way out to Pluto. And there can be events that can kick a planet out of the star system. If you have that three-body interaction, when a star passes through the solar system, it can kick up the orbits of the various planets and kick them out of the solar system. And now they would be rogue planets. They would no longer be in gravitational orbit around a star. They are just drifting, floating free in the Milky Way. Another possibility is that rogue planets could just form on their own, just out of, like if you have a cloud of gas and dust, but it's too small, but it still collapses, maybe it just turns into a rogue planet. You don't get a star, you just get a planet with several times the mass of Jupiter. Maybe it has exomoons that are orbiting around it as well. So it's been estimated that there are at least as many rogue planets passing through the Milky Way as there are planets orbiting around stars, which is pretty exciting. And there are other theories that there could be many more, like 10 rogue planets for every star planet, 100 rogue planets, maybe even more. And so in fact, the vast majority of planets in the Milky Way might be rogue planets and not just regular planets. That's unfair to rogue planets to not call them regular planets, but you know what I mean. But then do they suck, right? I mean, they don't have a star. That sounds terrible. Well, if the Earth was kicked out of the solar system and had to drift through space, the surface would cool down fairly quickly, freeze, and it would be a very bad day for anybody living on the surface of the planet. But below the ocean, things would remain fairly warm. You would have these hydrothermal vents at the bottom of the ocean that would be blasting out superheated water from inside the Earth, you would have nutrients coming up, and you would have an ecosystem that remained on planet Earth for billions of years, even as it drifted through space. But there's another idea that you can have worlds which are covered in water, but they have a very hydrogen-rich atmosphere, and they can maintain liquid water on their surface. They're called Hycean worlds. I did an interview with someone who has been sort of predicting these worlds are out there. And so you can have just a range of places where they're covered in ice to various thicknesses, and then like imagine if you took Jupiter and you put it out in the middle of space. You would have Jupiter and you would have Europa orbiting around it, and would still have those tidal interactions. It would be largely unchanged, whether it was in orbit around the sun or whether it was out in the middle of deep space. And so these places that are interesting and exciting to have life on them could be out there. And so this idea of a world that has a water, sort of a thick water surface and a rich hydrogen atmosphere, it's believed that these can still stay this way out in interstellar space. You know, they're not going to be great planets for living on, because you don't have a star that's constantly firing enormous amounts of radiation that you can use, but they're not going to be lifeless. And that's pretty exciting. And when you think about, if there are more of these rogue planets than there are stars, and we talk about, say, the closest star to us is Proxima Centauri at 4.2 light years away, well, there could be multiple rogue planets in between us and Proxima Centauri. They could be way stations to make a journey all the way to the nearest star. And so it makes these journeys between stars less difficult, because you've got these places you can fill up your gas and find supplies, which is pretty cool. Nigel Catterall: if primordial black holes exist and small, surely we could track them with their external temperature, as they should be hot. Yeah, this idea of primordial mass black holes are black holes that might have been formed at the beginning of the universe in various overdensities in the material that was present right at the beginning of the universe, really just a few minutes after the Big Bang at the most. And then these objects could be wandering around the universe, and maybe they're as big as supermassive black holes, and maybe they're as small as the mass of an atom. And everywhere in between, wherever you just got enough energy and density packed into a small enough area, you could have gotten a primordial mass black hole. And there's a lot of scientists are thinking these are serious, and they're searching for some kind of evidence that these things are out there. And one way to search for primordial black holes is to look for gravitational microlensing, where you watch to see as one of these black holes passes in front of a star and causes just a slight warping of the light from that star. And from that, you can sort of estimate the mass of the object that passed in front of it. And if you get a black hole that is less than the mass of a stellar mass black hole, something that is like, say, maybe 10 times the mass of the sun, something weird's going on. And nobody has found these yet, but there are these surveys watching for the lights of various stars to wink out briefly as a black hole is passing in front of them. But as you say, another way that we could detect these primordial mass black holes is as they evaporate. So a supermassive black hole is going to take like 10 to the power of 100 years to evaporate. So it's going to be a long time. What is that? A 1 followed by 100 zeros, years. The last thing to happen in the universe. Like maybe proton decay will be the last thing, but before that will be the black holes dying. But as the mass of the black hole gets smaller and smaller, less and less, then the temperature rises and the amount of radiation that's blasting out of it goes up. And it's estimated that in the lifetime of the universe, any black hole that is smaller than about the mass of an asteroid, like a small asteroid, will have evaporated over the almost 14 billion years, the age of the universe. And so this is another way that astronomers are thinking that they might be able to search for evidence that there are primordial mass black holes, is to watch them disappear, watch them evaporate in this final flash of gamma radiation. And this was one of the explanations that astronomers thought might be behind gamma ray bursts, that we see these bright, brief flashes of gamma radiation. What's causing them? One possibility is that these black holes at the very last few moments, when they're the mass of a house, when they're the mass of the car, then they're just going to last a few seconds, and then they blast out this flash of gamma radiation, and then they're gone. And these could be primordial mass black holes. But then we've definitely found evidence that they are colliding neutron stars, that they are really massive stars that are exploding, and there's not a lot of evidence that they are coming from primordial mass black holes that are evaporating. But no one has ruled them out. And they could also be an explanation for dark matter. So, I see a couple of papers a day on Archive with people doing additional research on primordial mass black holes. I've interviewed someone here on the channel. It's a pretty fascinating topic, and hopefully we'll get an answer to this question. I love the idea of that the explanation of dark matter is that there are primordial black holes left over from the Big Bang floating around in the universe. No, wait, I'm terrified by that idea. But I also love it. Triskelion. Oh, when you talk about red-blue shift, does that include frequencies beyond the visible spectrum? Absolutely. The electromagnetic spectrum, we think of radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays as separate things, but they're not. They're the same thing. They are the electromagnetic spectrum. They are photons. You are listening to photons of radio waves. You are feeling the warmth of infrared photons. You are getting a sunburn from ultraviolet photons. You are seeing through your skin into the bones with X-ray photons, and you are turning into the Hulk because of gamma ray photons. It's all the same thing. And whenever the object that is emitting those photons is moving relative to another observer, the photons are redshifted or blue shifted. The wavelength of those photons changes. And so back at the very beginning of the universe with the cosmic microwave background, it was originally red, around 3000 Kelvin. It was like the surface of a red giant star. But then over time, as the universe is expanding, as the regions have been moving away from us, the light that's coming from them has redshifted all the way from red through infrared into the microwave spectrum. And in the future, they will redshift into the radio spectrum. But you could do the exact opposite. If you hopped in your spaceship and you moved very quickly, as you were looking at visible light, perfectly safe visible light, it would start to blue shift into ultraviolet, and you could start giving yourself a burn, a sunburn from what was once visible light, thanks to your velocity. So for me anyway, there was this moment when I was taking physics at university when it really sunk in that all of these things that I learned separate names for were all the same thing, and that they're just different aspects of this same thing, the photon. Electromagnetic radiation. It is a spectrum, and these various wavelengths can shift from one to the other. All right, those are all the questions that we had today. Thank you, everyone, for asking your questions in the comments. Thanks, everyone who showed up for the live show. Reminder, we do this at 5 p.m. Pacific every Monday, so come join us. And don't forget to vote for the question that you thought was the best. All right, we'll see you next week. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word. There are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Josh Schultz, and Andrew Gross, who support us at the Master of the Universe level. All your support means the universe to us.